Everyone, welcome to this update to the Kumeu Observatory. I'm Tony Cooper. Some of you will know me. I've been doing astronomy for 50 years. I started off as a member of the Palmerston North Astronomical Society. My parents bought me a telescope from Graham Loftus. When I was a kid, I met Graham and also Grant Christie. So here I am, a member of Auckland. Been doing Kumeu since 2019 for the last 3 years, and I'm doing the Kumeu update. And in 3 years' time, it might be one of you doing the Kumeu update. Steve did the previous one in 2019, and it's quite interesting. It contains all the history of the Kumeu Observatory. It's in 2 parts, so you can watch them on YouTube. Just note the misspelling of Kumeu. It's spelled K-E-U-M-U, which isn't the correct way of spelling, but that shouldn't cause too much problems because Google seems to know it either way. This is the last slide of Steve's presentation, the future. And he mentioned 4 topics, so I'll cover those 4 topics. The future is here now. He talked about using a PIN code, and now we do have a PIN code on the padlocks. So anyone from the Astronomical Society can find the PIN code and go and unlock the gate and get into the building at Kumeu. We have people using the site now. Remote operation, no, that hasn't been implemented yet. That's still on the cards, and it's probably going to take a while to do that. But the most interesting thing is that we have a better camera. So those are the 4 points that Steve covered last time, and 3 of them have come true. So in this presentation, I'm going to give you an overview of the site of Kumeu, for those who aren't familiar with it. Then I'll update the equipment since 2019, and then I'll update you on the science that we've been doing since 2019. And some science on with the old camera as well. So the site, it's out Kumeu, it's on Tawa Road. It takes me half an hour to get there. That's what it looks like from the road. It's quite well hidden. That's what it looks like when you get on site. So there's 2 buildings there. One belongs to the dome, and the other one's a separate observatory. That's called the WASP Observatory. In 2010, we used to have meetings out there, and one thing we'd like to do in the future is have more meetings. So I think there's been a 10-year gap since those meetings. Be interesting to start having some presentations like that. So on the site, if you go out there, it's a reasonably dark place to do your own observing. There are 3 places where people go. On the right, on the top here, this is the courtyard, which is in between the 2 buildings, and you get a good view there. This one in the middle is near the top of the hill, and it gives you a good view out in this direction. And if you go onto the road, along the road here, there's plenty of grass, and you get a really good view out to the horizon on the west. Kumeu is a Porthole 3.9 site. If you know the Porthole Scale, that's reasonably dark. It's a lot darker than Auckland, like Stardome is 6.5. And it's almost as dark as other sites around the Auckland area. Not as dark as Waharau. And the 2 dark sky sites, Great Barrier and Mount John, are a fair bit darker than Kumeu, but not as much as Kumeu is darker than Stardome. I've done stellarium landscapes for 2 sites at Kumeu, and those are available from me if you want them. So this is the view of the sky from the courtyard, and you can see most of the sky, and this is the dome itself up here. This is the south, so you can see the South Pole, so you can do your polar alignment easily. And this one is the view from inside the dome itself. And this is the view, this is tonight's view. You can see most of the sky, but you can see that There are a few trees that do block the view. However, the best part of the sky is completely visible. If you want to keep stuff out there, there are lockers, and lockers are first in, first serve. If you try getting out there at sunset in winter, this is what the driving conditions are like. And so I avoid that. That's why I do the midnight to 4 a.m. shift and not the sunset to midnight shift. The main points of congestion are down here, and then this terrible roundabout at Kumeu. Just queue for hours at that roundabout, and then getting into Kumeu itself is quite an effort sometimes. So you have to watch out for that. And the same thing happens on Sunday afternoon. So if we have a working bee, it can be quite difficult getting out there at 1 o'clock in the afternoon due to traffic. And it's only going to get worse. Interestingly, these are the plans for the northwest, and they're looking at putting in a new motorway to bypass Kumeu. And the motorway goes exactly through the observatory. So it'll be a pretty quick drive to get to the observatory, hopefully. That might be a bit noisy. So the telescope. Steve covered the telescope in his last presentation, so I'll only cover the changes. We bought it from Astrons. And if you look at the Astrons website at the moment, you see that the price for these is $0, which means they're giving them away. So I'd suggest you get in pretty quickly there. This is an old photo from Steve's presentation of it being installed. I didn't actually get time to get a photo for this slideshow, so I've got a couple of old ones. And what we've done new is we've put a shroud around the scope. And the shroud's pretty good. It keeps out stray light. And we put it in particular because moonlight was affecting images quite a lot when the moon was around. Something new is that we're now using the fans. It gets pretty hot in the dome during the day, and there's a large temperature drop when the sun sets. And so I highly recommend using the fans to cool the mirror down, to get it cooled pretty quickly. Because if you don't do that, you notice strong focus shifts during the evening. Now, something that's interesting is that someone has posited that all these GSO telescopes, the Ritchie creations, have the wrong baffle length. And so this guy has a YouTube video demonstrating the problem. And I think that concerns us. And so there's a YouTube link up there. And what he's saying is that on bright nights on the full moon, you can't do photometry. And we've noticed that as well. That's one reason why we put in the shroud. But if this is true, then we may need to do some more changes to the scope. This is one of our flaps for the scope. So this is just an image of the blank sky, and it's highly stretched, highly exaggerated to see the dark and the faint areas. And in the center, it's kind of dark, and around the edges, it's kind of light. So it looks like there might be some light leaking in around the edges. So that's something to investigate for this year. And this is a diagram that he drew of all the light paths. This part here is the baffle, and it extends into the tube. And his suggestion is that we extend the baffle a little bit further. These are his recommendations, extending the baffling. And people are adopting those changes, and you can actually buy pre-made 3D printed parts for these various scopes. So it looks like there's some credibility there. So the next project for us is to collimate the scope. Collimation is a pretty tricky process, and I'll explain why that is. So in 2020, we started the collimation, and at that stage, our stars were looking a little bit triangular. Then a bit more work, and by 2021 we had stars that were looking much better, but a little bit elliptical. So hopefully 2022 we can have circular stars. Now the interesting thing is that photometry, where you're measuring the brightness of stars, doesn't seem to be affected so much by the shape of the stars. So the photometry is pretty good, and we've got proof that it's pretty good, and I'll show you the proof later on. But for doing ordinary photography, it's not good to have elliptical stars. Now, this is the James Webb Telescope, and this is the first image of a star that they took. And you can see that there's 18 stars there because they have 18 mirrors, and the mirrors are pointing in different directions. So they need to collimate their scope. All reflectors need collimation to make sure that everything's pointing in the right direction. And they're going to spend a considerable amount of time collimating this scope. They could speed up the time if they got Steve Henley to do it, but they don't have him, we have him, so they'll have to spend a month or so doing it. Now, I understand why the stars are in 18 different places, but I don't understand why they're not circular. So collimation of James Webb seems to be pretty complicated. This is our telescope, and this is a photograph of Sirius. And you can see that the circles aren't quite concentric, and there's a little bit cut out the left edge. So our collimation isn't perfect. When we're focusing, the idea is to move the focuser into the position with the smallest size of stars. And you get a V curve showing the star size, and the optimal focus position is where the V curve is lowest, which means the stars are smallest. But this V curve has a W shape. You have a drop down here and a drop here, and it goes up again in the middle. And this is a pretty consistent pattern, and it probably results from a lack of collimation. So it makes it tricky to focus. Should you focus at this point here, which is the lowest, or should you focus at this point here, which is a midpoint between the two low points, or maybe you should focus at that point. So it makes focusing a little bit difficult. Focusing isn't so important for photometry, because it doesn't matter if so much of the stars are a little bit larger in size, but it's quite important for ordinary photography. You can see the temperature of the focuser is 20.3 degrees, so the thermometer on the focuser works. Steve was asking about that. And an effect of the collimation is that stars, if they're not perfectly focused, they have an elliptical shape. And you can tell how far out the focuser is by the amount of ellipticity. So when the focuser is too far out, the stars are angled on this angle, about 45 degrees, and if the focus is too far in, the angle reverses. That's pretty useful to know, because if you're doing photometry during the night and you realize that the stars are starting to become elliptical, then that means you need to refocus. So it's quite handy, but it's better if it doesn't happen, I think. So this is a photo that I entered in the photography competition, and the stars look reasonably good. But if you look in the top left-hand corner, you can see that up here, the stars kind of have a pentagonal shape, and over here, they're sort of elliptical. So it's not perfect, but it looks pretty good from a distance. This is a Ritchie-Chrétien telescope. The light comes in on the left, hits the mirror, bounces up to the secondary mirror, and then comes down to the camera. To do collimation, you need to get 4 things right. You need to get the focuser tube pointing directly at the secondary mirror. You need to get the secondary mirror pointing directly at the focusing tube. You need to get the primary mirror pointing directly at the secondary mirror. And then you need to get the two mirrors the perfect distance apart. Because in a retticration, the distance between the mirrors is actually important. It's not for most telescopes, but it is for this. So you've got to get four things right, which is why it's taken so long to get the collimation right, and why it's an iterative process, because you adjust all four things and then it's not right. And then you go and adjust all four things again and go over it again and again. And each time you get closer and closer. But when you tweak one thing, the others all need tweaking in response. So you can't just do all the tweaks in one go. Focuser. We made some changes to the focuser. We added a temperature probe. We didn't have that before. We've stopped using Maxim DL for focusing, or I think Jonathan still uses it. Maxim DL likes to focus on one star. I like to use Nina because it focuses on more than one star, and I think it's a lot more reliable. So that's one. So those are two changes. This is the V curve you get from Maxim DL, and it's not a nice V. It's kind of almost a reverse J. And this is another V curve, and it didn't work at all. Don't know what went wrong there. So I've been using Nina. The big change during the last 3 years is the new camera. And it uses the Sony IMX455 sensor, QHY 600M. It's pretty much the latest and greatest camera that you can get. But the big difference between this and the previous camera, which broke down, is that this is a CMOS camera, and the previous camera, and the camera that most people use are CCD cameras. But this is CMOS, so this is quite new for photometry. It's difficult during COVID times to buy CCD cameras, and they don't make many of them anymore. And Sony mainly make cameras for things like industrial applications and cell phones and things like that. And all of those applications have moved to CMOS. And so they're not interested in making a handful of CCD cameras every year for astrophotographers, because Sony are just a handful. So the astrophotography industry is moving to CMOS cameras. So we've got a CMOS camera. Now, I don't have a photograph of the camera on the telescope, but this is one of Steve's photos. And you can see this camera here on the right. We've just replaced that with this camera here. So it looks pretty much the same, except it's got a red ring around it. The camera is full frame, if you know what that is, has full well capacity that can be quite large, up to 720,000 electrons, if you know what the full well means. It has 16-bit and up to 18-bit analog to digital conversion. So if you know what that means, most amateur cameras have 14-bit analog to digital. This one is 16 and goes up to 20. So that's pretty good. But we don't have software that can handle 20. Our software can only go up, Maxim DL can only go up to 16 as far as I know. I've tried higher, but I haven't got it to work. So the sort of standard camera, the standard CCD camera that the professionals use, and a good example of that is the KAI 11002, which is a CCD camera. It's in the specifications for that camera, manufactured by ON Semiconductor. They say it's a high-performance 11 million pixel sensor designed for professional digital still camera applications with high sensitivity and large full well capacity with high dynamic range. That's what they claim for their CCD camera. So let's compare our camera with that camera. So you can see that our camera has about twice the quantum efficiency as that camera. So our camera collects twice as much light. Dark current is current that comes from temperature inside the sensor, which is why you cool the sensors. But they still have dark current in there. And our camera on the left has almost no dark current, whereas the KAI has a fair amount of dark current. So ours is pretty good there. Read noise, that's just random error inside the camera. We've got a lot less of that, 3.7 versus 10. Dynamic range, we've got a lot more dynamic range. And download time. CMOS cameras are much faster to download the image. So this camera is pretty good compared to what the CCD cameras are using. So it seems inevitable that eventually people using CCD cameras will migrate to CMOS cameras. An important requirement for a camera is that it's linear, which means that the measurement, the pixel value, has to be linear in response to the length of exposure. And you can see that this camera is linear up to about exposure, up to about this value here, and it starts to bend off. And that's reasonably good, but it's not perfect. Now, at the other end, at the low exposure end, it's quite non-linear, and this is important for photographers who use bias frames. Bias frames assume that cameras are perfectly linear, and this camera is definitely not linear at the low exposure end, underneath 20 seconds. So if you know what a bias frame is, if you know what camera calibration is, and if you have a CMOS camera, you shouldn't be using bias frames. You should be using dark frames instead of bias frames. So that means dark frames, you have to take a dark frame at the same exposure as your light frame. So if you know about camera calibrations, then that's a warning about CMOS cameras. This is a pretty good camera, so if it's non-linear at the low end, then other cameras that aren't as good will probably have the same effect. Now, dynamic range is the difference between the brightest and the dimmest objects it can photograph. And for photometry, you want to be able to photograph light stars and dark dim stars as accurately as possible. So you want the most dynamic range. So this camera has different modes, has 4 different modes, and 3 of them are shown here in the in the blue, green, and purple lines. And so this shows the dynamic range as a function of the gain setting. So if you know what gain setting is, and if you know what dynamic range is, then the obvious choice for this camera is to use gain 0, which gives the maximum dynamic range, which should be the best setting for photometry. And you might think, well, here's another setting up here which has as much dynamic range as this setting here, so maybe we should use this higher gain. But if we go to the depth of the well, we see that this other gain has a lower well depth, which means it can't record as many different values. So it has wide range, but it can't record them as accurately. So we go for maximum range resolution by using gain 0. And that gives us a well depth of 50,000 electrons, which means it can record 50,000 electrons. So that's a bit technical about the camera, but some people listening to this presentation will understand what that means. So it was an obvious choice for this camera to use this mode 1, which is the blue mode, and to use gain 0. Once you know the gain, you do a plot of minimum pixel value versus your offset. The offset is an amount that they shift the image by so that you don't get negative pixels. And you choose the minimum offset that you can without going to 0. And so here our best offset is 10. So we use gain 0, offset 10 for this camera. A little bit technical, more information than people want to know, but of interest to people who are doing astrophotography with CMOS cameras. Another thing to choose is binning. binning. Binning means how you combine pixels. So you can combine 4 pixels into 1 pixel if you use 2x2 binning. And the optimal way to choose binning is to give you 0.5 arc seconds per pixel. So if we use bin 1, we get 0.24 arc seconds per pixel. Bin 2 gives 0.4 arc seconds per pixel. There's no point in going more accurate to smaller values than 0.48 because the atmosphere jiggles the image too much. And so you can't get resolution below 0.5. So that's why 0.5 is the recommendation. So Auckland's atmosphere is pretty good in that respect, and it can let us go down to 0.5. So we'll go to 0.5, but there's no point in going to 0.24. So that's the end of the technical stuff, how we set up the camera, gain, offset, and binning. Choosing the temperature, yeah, minus 20 degrees. Minus 10 would have done. In summer, when the outside temperature is 20 or more, the camera can't get down to minus 20. But that's, I haven't had that problem. I had that problem last summer, but I haven't had that problem this summer. So this graph shows that if you're cooling the camera, minus 10 is probably a pretty good cooling value. The images have, for calibration purposes, they have a black stripe along the left and along the bottom. So that's something to watch out for. And those stripes have specific purposes for scientific purposes. So one of my projects has been to work out how best to use those black stripes. This doesn't affect many people because not many cameras have these black areas, but I suspect that increasingly CMOS cameras will have them. Just a couple of pointers from QHY, the manufacturer, is saying don't cool the camera too quickly. So we cool it down over 10 minutes. The CCD cameras we had before, we just cooled them as quickly as they would go, but they're saying that if you cool it too quickly, you'll damage the camera. So thermal shock will damage the camera. So cool these cameras down slowly and warm them up slowly. Strange thing about USB traffic. If you have the USB traffic set to the wrong rate, you get banding in the images. I don't understand that. And you can't remove it. So yeah, you have to adjust the frequency of the CMOS sensor driver to get rid of the banding. Pretty tricky, but I haven't noticed the banding. But it's something to watch out for. Now, this is an interesting image that I've taken of Sirius. And if you're experienced, you say, well, what are those lines? We know that 4 of those lines are caused by the vanes that hold the secondary mirror in place. But what's the extra set of lines? So you might want to wonder about that, and I'll explain it later. Oh yeah, I'm explaining it now. The extra set of lines is caused by the telescope not pointing perfectly out of the dome shutter. And so the dome shutter sort of intrudes into the photo in only a very small number of positions. So that's why it took so long to diagnose this problem. And so two of those lines are due to the telescope, and one of them is due to the shutter. If you point the telescope completely halfway through the shutter, and so the shutter's halfway across the telescope, you get this shape. So that's a warning. If you're imaging and you notice this shape or this shape, then it's time to move the shutter. And this is I call this the Zorro Nebula. For some reason, Maxim DL, the first image it takes from this camera, it has all these Z shapes in. And if you take a 15-minute exposure and it has these Zs in, you can feel a bit annoyed. So what you need to do is to take an exposure with the camera first, 10-second exposure. And for some reason that warms up Maxim DL, so it's ready for the remaining exposure. So the first exposure that Maxim DL takes from this camera tends to have this pattern in, and It's a bit annoying, so you have to be ready for that. The filter wheel, it's interesting. This is what the filter wheel and the camera looks like. This little camera up here is a guide camera, and we use that for guiding. If you know how that works, then I should perhaps put in a diagram to explain that, but I haven't. So this intercepts, has a little prism that intercepts light coming towards this camera so that you can look at stars and see if they're moving while you're taking an image. And if they're moving, then you need to adjust the telescope to follow them, because it means it's not tracking the stars properly. But this is what the filter wheel looks like here. And inside, it looks like this. There are these filters. Now, notice that these filters are screw-in filters, and they have a rim on them. So these filters are 48 millimeters in diameter. And they are perhaps, one thing we suspect is that they're a bit small. And so when you take images, the corners are dark. And this chart shows the brightness of the image. And it shows that the images are quite dark in the corner and also dark, a little bit dark in the center. So we suspect, we don't know for sure though, that the filters are causing that imaging. What we should do is have filters that don't have the screw-in rim. And these are 52 millimeter filters. And so they're slightly larger and they let in more light at the corners. They don't screw in, so you have to put in these little fancy red things to screw them in. So when we upgrade our filters, we may buy some new ones that are bigger. The dome was quite interesting. The dome works on a pulley system, and there are pulleys and you pull on a rope. And it's always been quite tricky opening the dome. And so when you open it, the dome comes down, and so in this direction, and then it stops here, and it's supposed to stop here. But what was happening during the year was the dome was getting stuck. And it's important not to open the dome too far, otherwise it falls off, because there's nothing to stop it falling off. So we used to open it at a certain distance. But then at the top, it was getting stuck. And every time we closed the dome, you'd have to wind it backwards a little bit to get it over the stuck point. And so build up momentum to get it over the stuck point. And one night I was imaging and I came to close it and I went too far. And so it came off and then it just dangled on an angle like that. So had to phone Jonathan, he came out, and then phoned Steve, and Steve came out, and then we sort of messed around and we had to put the shutter back on its rail. So I felt pretty bad about that because it was me who wound it back too far. So we put it back on, and then Jonathan tested it out, and then he wound it back too far and it ended up back in this position. So it made me feel a lot better about it. So we got these guys in, and they put a stop so that the dome couldn't go too far. But that didn't solve the problem at the top. The problem is you can see that these wheels, well, you can't see, but these wheels aren't properly aligned, and this wheel is in the air. And I think one of these wheels was hitting this bracket here, and that was causing the bump. So we got Peter McLeod in. He's the friendly neighbour who comes in and does repairs for us. This is him doing some repairs on the observatory in 2010. And he fixed up the wheels so that the shutter now is quite safe to open and close, and it doesn't have that hard bump at the top. Other changes with the camera, we had to kind of change. Maybe it was a collimation, or maybe it's the camera, but we had to introduce new software because Maxim DL wasn't doing a good job. So for guiding, we switched to using PhD2 for guiding, and for focusing, I'm using Nina, and Nina has a setting that lets you warm the camera up over 10 minutes, whereas Maxim DL just switches the camera on, the cooler on, bang, which isn't good for the camera. And the camera has a humidity sensor, and so we can use the QHY EasyCap QT software for checking the humidity in the camera. And I've filled it up, it has a desiccant tube, and I've filled it up with desiccant. And I've used coloured desiccant, so it's orange when it's dry, and when it needs replacing, it turns green. But our biggest problem is Maxim DL, which is still used for imaging, crashes. And you get a few crashes during the night. And this is just an example of one of them. And the crashes occur quite randomly. You could just be sitting looking at the screen, not touching anything, and it's just spontaneously crashes. Or you could be clicking on something and it crashes when you click. So it's quite scary. All we can do at the moment is just hope. I suspect that the problem is in the camera driver rather than Maxim DL. So the interesting stuff is the science that we're doing. So just to make it clear, if you're a member of the society, you can come out and use this telescope for your own photography. You'll need a bit of training, and you can do anything that you like and photograph anything that you like, provided it's not being used for science. Science takes priority, and we like people to come out and do science as well. And if you like the idea of doing science and putting yourself up as a Nobel Prize winner, then come out and do science. So far, the science we've been doing is microlensing. So I'll explain what microlensing is. Photometry is the measurement of the brightness of stars. And this is what a typical target looks like. The lines here show this little tiny star in here. And what we're doing is we're measuring the brightness of that tiny star by taking multiple photographs. And we photograph them all during the night. So what happens is there's a target that astronomers around the world want to observe 24 hours a day. So all the observatories in Chile monitor it for a few hours, then New Zealand monitors it for a few hours, then Australia, then South Africa. So on a 24-hour cycle, we can get most of the 24 hours by each country chipping in a little bit. So Kumeu chips in along with Star Dome and Farm Cove observatories. Microlensing is one of the methods for detecting planets that go around other stars than our sun. And they're difficult to detect because you can't see them. And also you can't see the star that you're observing. There are hardly any stars that you can actually see as a disk. They're just tiny points of light. So you've got to use indirect ways of detecting them. So microlensing works like this. This is the Earth on the left. This is a star. And this is another star. Now, stars have gravitational fields and they bend the light. So the light from this star comes out here and gets bent towards the Earth. So this star here, the gravitational field acts as a lens and acts as a magnifying glass. So this light here would normally go out here and we wouldn't see it, but it gets bent down to here. And so we can see it. So it looks like this star here is like this. We just go out and we can think this star has the extent of here. So the way that it works, this is a better way of showing. This is a star in the background. This is a star in the foreground. And this is a planet going around the star. This star goes in front of this star, and the gravitational field starts bending the light. and magnifies it. And this planet has its own gravitational field, and it distorts the magnification. And so this distortion is a little blip. It's an extra blip of light on the brightness, and then it goes past. The same technique can work for black holes. So a black hole can move in front of a star, and a black hole, which you can't see at all, distorts the gravitational field, and it produces this kind of effect. So this is an interesting bit of science from 2011. Observations of this black hole moving in front of a star were taken around the world in 2011, and some of those observations came from Kumeu. So they came from the old telescope and the old camera. And but last week the results came out, because they had to then do some follow-up observations using the Hubble telescope. And last week the results came out, so it's interesting. So we started observing in 2011, and just last week, just in time for this presentation, the results came out. Astronomers found a rogue black hole adrift in the Milky Way. So this black hole is just floating around, not attached to anything. And because it passed in front of a star, we discovered it, and Kumeu took part in those observations. So this is the light curve. These are the light curve from the observation. The star in the background slowly gets brighter and brighter, then zips up really bright when the black hole goes right in front, and then dips down again. And you can see here, I've marked out Kumeu's observation. And they're yellow, so that's the Kumeu observations up there, and it's Kumeu observations there. So Kumeu took part, and we get credit for that. But this is the more interesting one. The very first night that I started doing observations by myself at Kumeu, we were observing this target. And then after I'd finished, and the next night, I think, Andrew Marmont came in. We thought the event was over, and he came in to take an hour's worth of observations to normalize the data. They're just observations when the event is finished, so you compare them with observations when the event is on, so that you can figure out the differences in brightness. So he contributed some observations from Kumeu that uncovered this planet. And because of that, in this paper, he gets the title of leading authors, Andrew, Jonathan, and Steve. So that was lucky for me, because it's the first time I did any microlensing at Kumeu, and we were part of this discovery of this planet. So that's quite good for me, good for Andrew, and increased my enthusiasm. So this is the light curve from those observations, and these purple ones are the Kumeu observations. So you can see it goes up, then down, and then there's a big blip. You can see down here a blip, and this is just 1 hour of observations from Andrew. And so you can see he came in at just the right time. If he'd come in 2 hours earlier, would have missed, and if he'd come in an hour later, would have missed. He came in just at the right time to make the observations to discover this planet. And this is a close-up of those observations. Without them, there would be no blip and no planet discovery. Last year, and this one has my name on it, we were part of a discovery of another planet. So in the 3 years I've been there, we've discovered 2 of these exoplanets. And this is a light curve, and these are my personal observations here, Kumeu and Brown, and those are the ones I did on my night. And I think those ones, these ones are Jonathan Jonathan's observation, but those ones are mine. So got my observations in a scientific paper. So if you've got a scientific bent like I have, then that's a little bit exciting. So maybe in 2022, your name will be on one of these papers and you might be eligible for a Nobel Prize. This is how Steve ended his presentation with the future, and he listed 4 things that he hoped to achieve, that we hope to achieve in the future, and we achieved 3 out of 4. So this is the new list. This is my list of things for the future. Future collimation, so we get circular stars. Remote operation, that's always going to be on the cards. And we'll start there by motorising the shutter, I think. But that's beyond any of us. That requires engineering. So it's a big project, and it may or may not be done this year. Science filters, our filters are RGB filters, whereas science filters use UV-VGRI. So we're talking about getting a set of science filters. For photometry, they like the V filter, which is similar to a green filter, but it's not. And we're interested in new science projects. So at the moment, we're doing microlensing, but there are plenty of other scientific things that we can do, and we'll be looking at those. And if you're interested in doing science and you have some good ideas and you want to do amateur science, then we're open to ideas and we'd like to see you, and we're quite happy to train you. And if you just want to come out and do ordinary photography, photograph the Orion Nebula, we're happy to do that and happy to train you. So think of this as your observatory, our observatory. Stay in touch, kumeu.blogspot.com, facebook.com, and the address is 335 Tara Road, Kumeu. So now can take questions.
There are no questions so far in the chat. There is a little bit of time if anybody wants to throw any questions in there. I'll ask you a question though. So you said that your first night was, when you first started, it was when we had the planet discovery. What got you first excited about joining the Kumeu team?
I think it was when I first knew that Kumeu was there. I knew it was there before I joined Auckland, and the main reason for joining Auckland was so that I could use the Kumeu site. But at that time, I didn't think of using the telescope because I didn't know the telescope. I didn't know what was inside that building. I just knew from Facebook. No, I think from, because I never used Facebook, I think from the Astronomical Society main webpage, I knew that Kumeu existed. And I went out there once and had a look, and the gate was open and someone was there, and I went down and had a look. I didn't know that at that stage the gate was padlocked, so I thought it was just open to go anytime. So the first time I went there, the gate was locked, so I just climbed the gate with my telescope and just used it. But I'm a mathematician by trade. I'm a scientist by definition. I'm always interested in science, and so I'm interested in the more mathematical side of astronomy, as you could tell, and the mathematical side of astrophotography and all the science of light curves and things like that. So I was interested ever since I was a kid. I lived in Palmerston North, visited Auckland. Graham Loftus is related to me in some way. So my grandparents took me to visit him, and I spent quite a few hours with him and also with Grant Christie.
Thanks for that. And yeah, we got a couple of questions in here. Gabrielle wants to know about the remote observatory idea. Would members of other societies have a chance of using it, or is this exclusive to the Auckland Society? probably the case, but worth the ask.
Yeah, it's not a question that I can answer. Um, I think that people, even in Auckland, would have to queue up behind me. I think I would grab it first just because I quite like the telescope and the camera and everything. So it might be difficult for other people to get an eye in. The ideal situation would be for me to be using it remotely at home while using my own telescope remotely at home. But, science comes first, and I can't do it all on my own. And we need a team out there doing 4-hour shifts. So um, I would imagine that during winter, depending on what's going on, it may or may not be difficult to grab a slot if it's remotely operated.
Thanks, Tony. I'll probably add to that. Gabriel, if you've got some ideas for things that you want observations on, particularly if it's science related, from another society, then yeah, absolutely get in touch, because we're always looking for ideas. The remote observatory thing could be tricky, but who knows what the future holds. Another question from Jenny McCormick. She says, "Hi Tony, MaxMDL can be used to slowly cool down the camera. There's no need to cool it down in one go." So I'm not sure whether that's possibly just for the QHY driver though, Tony. What do you think?
No, I think it can. I have a script. But I haven't figured out how to run a MaxMDL script to cool down the camera. So yeah, it's possible if the script works, but I haven't achieved that. And it's quite a nuisance using Nina to cool it down, because when you switch from Nina to MaxMDL, which you do for observing, that works okay. But when you switch from MaxMDL to Nina, Nina wants to warm up the camera as soon as you switch to Nina. So Nina doesn't respect, or I haven't figured out how to get it to respect the current temperature of the camera and to realize that it's already cooled.
Oh,
So
Jenny,
getting
perhaps
Maxim
you
to
could
do,
help us out and let us know how you've got the slow cooling down working in your observatory.
yeah, that'll be good.
No more questions. Just a comment from Danut, who's in Tokoroa, who says that he misses us. Who's a Auckland Society member who's now down country. But that's it for the questions. Thanks very much, Tony. I really enjoyed looking at the update. And it was great to see somebody else doing it. And let's hope we can tick as many off your future list as we managed to tick off mine from a few years ago.
Okay, you're welcome.
Thanks very much. Have a good night.